Hi everybody, today we're going to be talking about topic 1.3, elemental compositions of pure substances. As a little vocabulary reminder, remember that pure substances are matter that has a fixed composition and distinct properties. And so if we look at our matter chart here, pure substances are composed of either elements or compounds. Now, what do I mean by a fixed composition? What I mean is if you have carbon dioxide or CO2, it's always going to have one carbon and two oxygens. Now, this is spelled out directly in the law of definite proportions, a law that states that the elemental composition of a substance, in this case, when I say substance, I mean a pure substance, is always the same. If you have carbon dioxide, it's always going to be made of one carbon and two oxygens. If you have glucose, it's always going to be made of 6 carbons, 12 hydrogens, and 6 oxygens. It's always going to stay the same if it's a pure substance. A few other important terms that you're going to hear are molecular weight, sometimes abbreviated as MW. This is the sum of the atomic weights for the atoms in a molecule. So if I have CO2, for example, I would add up 1 carbon plus 2 oxygen and get my molecular weight. You'll also hear the term formula weight, or FW. And this is the sum of atomic weights in a compound. Now, you may be questioning what's the difference between a molecule and a compound. We must remember that in a molecule, we only have, switch my color here, in a molecule, we only have covalent bonds. Whereas in a compound, we can have ionic bonds as well as covalent. And so when I say a molecule, I typically mean covalently bound compounds. When I say a compound, this is ionically bound compounds or salts. Salts, otherwise known as something like NaCl, sodium chloride, which are ionically bound to each other. Another term that you're often going to see in a lot of AP Chem problems is empirical formula. The definition of an empirical formula is a chemical formula showing only the simplest ratio of elements in a compound. And essentially, these questions will typically give you a percent composition, where it'll tell you the percentage of each of the individual elements within a compound. And this data is normally generated by combusting an element and then getting the percentages of each. And we'll see in this next example here how we can calculate this empirical formula using percent compositions. So this would be an example of when we use a percent composition or elemental analysis. Ascorbic acid, or vitamin C, contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. What is the empirical formula of ascorbic acid? And so this would be a typical readout that you would get from one of those combustion devices to tell you the percent composition of each of these elements in a molecule. It's really good for you analyzing unknown compounds to try to see what's inside of that unknown sample. So first you would start by just assuming you have 100 grams of sample. This is really easy, right? Because we have a percentage, so it's out of 100. And so if you assume 100 grams, it makes the math very easy. 2, convert to moles, right? We always want to make our comparisons between different elements using moles. And so for that, we would basically just take each of these percentages, and since we're assuming it's 100%, we would multiply 40.92 grams of carbon times molar mass of carbon, or divided by the molar mass of carbon, which will be 12.01 grams of carbon per 1 mole of carbon. And that would get us 3.407 moles of carbon. Same thing for hydrogen, 4.58 grams of hydrogen divided by the molar mass, 1.008 grams of hydrogen, 1 mole hydrogen. Similar to the carbon, right? Grams cancel out. We end up with 4.54 moles of hydrogen. And lastly, for oxygen, 54.50 grams of oxygen divided by the molar mass, 16.00 grams of oxygen, 1 mole of oxygen. Cancel, cancel, and here we get 3.406 moles of oxygen. And so now that we have our moles, what we would do is we would next, step 3, divide each by the smallest number of moles. And so in this case, the smallest number of moles that we have is 3.406. I'm going to highlight this in red, actually. Right, 3.406, 3.407 is pretty much the same, but that is the smallest number of moles that we have. And so what we would do is divide 3.407 moles by 3.406 moles, and this would be for carbon, correct? And this essentially just about is 1. We can do the same for hydrogen, 4.54 moles divided by 3.406 moles. We get 1.33. And then finally, for oxygen, right, since we're dividing by oxygen, we should get 1. 3.406 moles divided by 3.406 moles is equal to 1. And now for our final step here, step 4, what we would do is multiply to get a whole number. Right, and so anytime we see a chemical formula, an empirical formula, we don't see fractions or decimals inside of that formula. All we see are whole numbers. And so in a problem like this, you might be able to just say, well, 1.33 times 3 will give us a whole number. But if you want kind of a more formulaic way of thinking about this, or an easier way, what you can do is just convert all of your decimals into fractions. And so for C, this would equal 1, which is equal to 1 over 1. For H, this is equal to 1.33, which is equal to 4 over 3. And for oxygen, this is equal to 1, which again is equal to 1 over 1. And so if you want to get a whole number out of these for our empirical formula, what you could do is multiply 4/3 by 3 over 1, and then multiply our other elements by that same ratio. So for carbon, 3 over 1. For oxygen, 3 over 1. And what we get here for carbon is this would equal 1 over 1 times 3 over 1 is 3. For hydrogen, 4 over 3 times 3 over 1 is, the 3's cancel out. It is 4 over 1, which is also equal to 4. And same thing for oxygen, it would equal 3. And so our empirical formula for ascorbic acid would be C3H4O3. So this is the simplest form of the molecular formula of ascorbic acid. Now, as a reminder, right, that was the empirical formula. And so that is the simplified version of the molecular formula. So if you want to take the empirical formula and get the molecular formula, we have to use the molar mass of our compound of interest in order to calculate that. And so what you'll do is first find the mass of the empirical formula, again, by just adding up each of the elements in that compound or molecule. Then you would divide the molar mass of the empirical formula, which will always be given to you. I'm going to highlight that in red, actually. Right, so this, always given. You'll divide the molar mass of that empirical formula, which is given to you, to find the ratio between the molecular and the empirical formula. and then you'll multiply all of the atoms or the subscripts of those atoms in the empirical formula by this ratio. And I'll show you how to do that on the next slide. So in this next example here, we have mezidoline, which is a hydrocarbon that's found in crude oil, has an empirical formula of C3H4, and an experimentally determined molecular weight of 121 AMU. And this question is asking us to find the molecular formula. And so using that process that I was showing on the last slide, what we can do is add up all of the atomic weights of our empirical formula here. And so this would be, for C, it would be the subscript is 3 times the atomic weight of carbon, which is 12.01. And then you would add that to hydrogen, right? So for hydrogen, this would be the subscript is 4 times 1.008. Right, so 3 times 12.1 plus 4 times 1.008. That would get us 40.06 AMU. Right, and so that is a molecular weight of our empirical formula. What you next want to do is divide the real molecular weight, which is experimentally determined, by the molecular weight of the empirical formula. So we do 121 AMU divided by 40.06 AMU. And this will give you that ratio between the empirical formula and the molecular formula. And if you do this math, you get 3.02. And so the ratio between the empirical formula and the molecular formula is about 3. Now, this isn't exactly a whole number, but it's very, very close. If we had gotten something, for example, such as 2.3, right, this is not close enough, and something went wrong in our calculations beforehand, and so this would not work out. But because our number is very, very close to a whole number, in this case 3, what we can do is multiply each of the subscripts in our empirical formula by this ratio. And so for C, it would be C 3 times 3, H 4 times 3. And so our molecular formula would therefore be C9H12. And this would be the correct answer there. Now, this is a similar problem to what we were encountering in 1.2 with mass percent, but you might also get a question like this on the AP exam, which is asking you to find the percentage of carbon in a compound. So in this case, the percentage of carbon in ethane, C2H6, which has kind of this formula here, CHHH. Not that you need to know this, but more so if you're curious, the percentage of carbon in ethane, this compound right over here. This pretty simply can be solved similar to what we did with the mass percent and also similar to what we did on the last slide, where we essentially first add the atomic weights to find the molecular weight. MW, the molecular weight, and then 2, find the atomic mass of element of interest. I should say find the total, right? And so in this case, if we're looking at carbon, we'd get the atomic mass of carbon and then multiply that by 2 to find that total mass of our element of interest. And then 3, divide mass of element of interest. In this case, I'm going to say mass of X by the molecular weight. And so for this problem, what we would do, right, carbon is equal to 2, because we have 2 of them, times 12.0, which would equal just about 24. And then for hydrogen, right, we have 6 hydrogens, so it'd be 6 times 1.008. Again, I'm going to round here, about 6.0. And so C2H6, its total molecular weight, would be about 30. I'm not being exact here, but it would be about 30. And if we want to find our percent composition of carbon in the sample, what we would do is take the atomic weights of our element of interest. So in this case, we have 2 carbons times 12, because that's the approximate atomic weight of carbon, then divide it by the total, 30 in this case. And then our percentage would be, oh, and I forgot, multiply by 100%, right? Because we're finding a percentage, not a decimal. And our answer would be just about 80% carbon. I'm not being too precise in this case, mostly because we've kind of seen something similar in the mass percent. But if you're ever asked to find the percentage of a atom in a particular element, this is the formula that you would use and the process that you would go about it. We'll do some more practice in class, but that's all for now. Thanks, guys.